exercise, but I also want your undivided attention. You know what undivided attention is? Physically and mentally present here, right, for the next 30 minutes, right? Right, so let's look at the member. The problem is use ASD and LRFD methods. ASD is allowable strength design and LRFD is load and resistance factor design. Methods to determine the available strength of CFS built up I sections as shown in the figure to be used as a compression member. Right, so this is the figure. Assume that the effective length factor K is 1.0 for x-axis and y-axis, and that the unbraced length of x and y-axis are 3.65 and 1.8 respectively. Right, so one side it is going to be 3.65 and another side it is going to be 1.38. You see this one, when it buckles like this, right, or it buckles like this. And use Fy equal to 350 MPa and galvalume coating as AZ 200. The intermediate fastener spacing is assumed to be 300. So we are putting some fastener spacing that is going to be 300 mm. So every 300 mm there is some kind of a restraint that you will have. Right? Any questions on this one? Right? We'll go slowly. So this is the built up section. Right? So the depth is 200 mm, the lip is 15 mm, and this is 75 mm. So back to back built up section. As you said, the screw is in one direction, other direction. This is 2 mm, right? Now we know that R is 1.5 T, right? We know that T equal to less than 2, so it becomes 2.94, right? How do we do so? Because the total thickness is 2 mm and the coating thickness is 0.043. Hopefully you have been taught 0.043, right? How to calculate the total thickness. Now base metal thickness is the actual structural thickness, right? That becomes 2 minus 0.043, it becomes 1.957, right? Now you transform this section, this 200 becomes 199.96. and this becomes 74.96, the thickness is 1.957, the lip is 14.957, right? Any questions on this one? Okay. So R equal to 1.5 T, so T is 1.957, so you multiply, you get 2.94, that is the radius. Now the steps to be followed is, first we have to calculate the section properties. Next, determine the nominal strength of the section due to global buckling. Third one is nominal strength of the section due to local buckling. Then determine the nominal strength of the section due to distortional buckling. And determine the axial strength, compression strength, taking the minimum. Right? So we don't know whether global is going to govern, we don't know local is going to govern, we don't know distortional is going to govern. We'll find out everything and choose the least one, right? So now the section property is required to find the strength of a compression member. For a single section, it is given like this, right? Now what do we do after this one? We have to calculate using this formulas here. So the flat length or width is what we have to find out. The flat width is actually the total width minus the radius, right? The corner radius that you have to find out. So the flanges is 74.96, we have 2, right? R plus T by 2, we have to take it out. R plus T by 2, because the thickness by 2 we have to take it out, so we will get the flat distance. So 74.96 minus 2 into R plus T by 2 is 67.12, right? Next, we will also find out web, it is 199.96, again minus 2 into R plus T by 2, it becomes 192.12. Right, that becomes the web. The third one is the lip. Here it is only one radius is there, so you don't multiply by 2, you multiply by 1. So this becomes R plus T by 2, 11.02. So one is called A, and this is called B, and this is called C. Right? Now you go to ASI CFS Design Manual, page Okay, 151, you get all these gory equations. It's not very difficult. It's just strength of materials equation. You can plug it in your Excel sheet once you have programmed it, or you have MathCAD, you put it in, you will get it. Piece of cake, not a difficult thing. Right? So you get the section properties. Now using these section properties, right? Cross-section area, Ix, and then you have this for channel section is like this, hat section is like this, and X bar for channel, centerline, web line, all these things, moment of finish, Iy, and there is something called M. You do all this, calculate this, and you get this properties for this one by having this. So A is there, Ix is there, Iy is there, Rx, Ry, X, C bar, M, all these things are defined here. X0, J is the torsional constant, 917.27, warping content CW is given by this one, Eg. Right, very simple, but these are all for singly symmetric cross sections. Now how do you go from here to doubly symmetric cross sections, right? Sectional property is required to find the strength of a member. For built up sections, you have A equal to 2 into AI. So 2 into 717.59, it becomes the double the value. X0 equal to 0 because it is doubly symmetric, and Ix equal to 2 into Ix individual, right? So we get 2 into 4.06, this is what we have, and then we can find out Rx equal to Ix by A, right? So we get this one, this is 75.22. Now Iy equal to the parallel axis theorem, right? AH square will come, right? So 2 times this, so 2 into Iy bar individual plus Ai individual plus xi square. When you do the numbers, it is 2 into this 0.49 into 10 power 6, which is Iy, plus A individual cross section 717.59 plus this distance. This is the xc bar distance plus the thickness divided by 2, which is xi the whole square. When you get this, you get 1.59 into 10 power 6. That is the Iy for the built up cross sections. Now Ry equal to Iy by A, root of, right? Now when you do so, you get 33.28 is the value for Ry, and that is for this cross section here. So you have to calculate Iy and then you calculate Ry, and this is the section property for the combined section, not the individual section, combined section, right? Any questions so far? Now, after having done that, for built up sections, you have this one, J equal to 2 into Ji. Ji is the individual, right? So you can add that one. So 2 into 917.27, you get this value, J becomes 1834.54, right? CW, warping constant, is also 2 into CWI, you get this value, 7.48 into 10 power 9. So you have increased this one, J is added, CW is added, right? The new values. Any questions on this so far? Right, now you have to calculate R0. R0 is Rx square plus Ry square plus X0 square. So X0 is 0 here, so you have 75.22 plus 33.28, which we calculated, plus 0 gives you R0 equal to 82.25, right? Now you got R0 also. Why do we calculate R0? There is a reason for it. Because we have to calculate PT, which is the load due to torsional buckling. That includes R0, right? So without R0, you cannot go further. So we are slowly building up, right? So let's look at it. The nominal axial strength P&E for yielding in global buckling, right? So find elastic critical buckling stress, that is our objective. We have put all the properties that we have calculated here, Ag, Ix, Rx, Ry, Xc bar, M, X0, J, Cw, Eng, right? All these section properties, including the metal properties, are here. Step 1, our objective is to find out FCRE. But our major objective is to find out P&E. P-N-E. What is N and what is E? What is P? What is that P?
Load.
Yes. Axial load. Okay. What is N? Nominal. What is E? Euler. Correct. Right? So Euler. Why not O? Why E? Yes. So you have to spell it as Euler, you have to write it as Euler. English is a funny language. Right? So you have to spell it as Euler and write it as Euler. Right? Now that E stands for that. What is the meaning of nominal? When somebody says nominal strength is this, what do they mean about nominal? What is that? Without any factors. So uncorrupted. The moment you add water to milk, it gets corrupted, right? So that's not nominal. So nominal is without adding any factors of safety, right? The purest form is nominal, right? So that's why you call the word nominal. So ASI S100 appendix 2 gives you all these equations. So it says that FCRE, right, is equal to PCRE divided by AG, right? Very simple. But now how do you calculate PCRE? PCRE shall be taken as products of PT as design and calculation, including the influence of holes if applicable, right? So now let's calculate PT. Right? What is PT? PT is for torsional buckling load, right? It says for doubly or point symmetric cross section subjected to torsional load. What is doubly? It's an I section. Here we have two C channels, so it becomes an I section back to back, right? What is point symmetric? Z sections, but here we are not dealing with D sections, so we are dealing with only I sections. So this one is the equation for that, 1 by R naught square Gj plus pi square ECW divided by KT LT the whole square. Here Gj is called torsional rigidity. What is ECW? Warping rigidity. So what does it tell you? This torsion load is actually a contribution from torsional rigidity and warping rigidity. Both of them are contributing to resist the applied torsion. You understand what I'm saying? So that's why there are two things. Now this R naught square we have already calculated it, right? So when we do so, we know that R naught is equal to 82.25, right? So we put this value, G is 0.78, from here 10 power 5 plus pi square, okay? So in J is 181834, right? The J is 2 times of something, right? So 900 something, 2 times you get 917 something, so you get 1834 plus pi square. E is given as 2.03 into 10 power 5, CW is given as 7.48 into 10 power 9 divided by 1800. 1800 is because, yes, actually there is a restraint there. Instead of 3600 you take 1800, right? Any questions on this so far?
Repeat the equation 1 by E R naught square.
1 by?
A.
Okay.
That's what we are mixing capital E.
Here is 1 by?
So 1 by R naught square.
Here is 1 by R naught square. So 1A is 1 by R naught square. So this is from this equation, right? So we are just following the code. So we get PT equal to 704.88. This is a torsional load due to buckling. Now next one is, it's not, that is 1A. Next one is we have to find out PCRE. Right, it says pi square EI by KL the whole square. Now it can be KX LX the whole square or KY LY the whole square. We don't know which one it is. It can buckle, fluctual buckling can happen in minor axis as well as major axis. We don't know what it is. So let us find out both, right? Now we have PCRE equal to pi square EIX by KX LX the whole square. So what do we do here? Pi square into E. This one IX is 8.12, which we have already calculated here, into KX. K is 1 into 3650. So in major axis it is buckling as the whole, right? In minor axis it is buckling this way, right? So major axis, what is the advantage? You have a greater IX, but the disadvantage is the length is more. In minor axis, the advantage is it has a shorter wavelength, that S curve is coming, right? because of this nogging or blocking or whatever you are doing, right? Bridging, blocking, nogging, it's all bracing, right? But the difficulty or the disadvantage is that the moment of inertia of Iy is smaller, right? So when you do all that stuff, you have to calculate for both P critical Ex as well as P critical Ey. So you have this pi square equal into 2.03 into 10 power 6, 10 power 5 into 8.12 into 10 power 6 divided into 1 into 3650, right? So we get 1221.14 kilonewton, right? Any questions on this one, right? If we don't have any questions, we'll go to the next slide. So next slide is we have to find out PCRE is this, FCRE is this. Now we have to find out 1A is that, but 1B is KYLY. Right? Previously it is KXLX, now it is KYLY. But this E into not IX, it is IRY. So there is a change that you have to do. Right? That is given by this class ASIS 100. It says chapter 1. When you do this one, this is what you have to do. Why is this change? Why not we use IY directly? Why I have to use IRY? What is the reason? You understand my point? Question? When it comes to IX, we are directly using it. When it comes to IY, we are saying that no, don't use like this. You have to use a different this one. What does it say? It says that, right, 1C IY into KYLY by RY divided by KYLY by RY square plus A divided by RI into Y the whole square. What does it mean actually? What is A in this equation?
Spacing between the fasteners.
Fasteners, spacing between the fasteners. So it is not 100% continuous, right? It is a discrete fastener, right? The fastener spacing is A, and so you should take into account if you have more wider fastener spacing, it will have less. If you have closer fastener spacing, the strength will be more, right? So that has to be taken into consideration. So they say that you have to use this parameter A by RIY. RI is the individual, right? R, which is the radius of gyration, individual radius of gyration in the Y direction. What is individual for a single cross section, right? So you have to do that. So when we do so, A is the fastener spacing here. In the problem, we know that it is 300 mm, correct? So now we have this IY is 1.59, 10 power 6, right, into 1 into 1800, because here it is, the nogging is there, so it have a double curvature, sinusoidal curve. So you have 1800 is the spacing, and RY is 33.28, which is already given here. This is for the combined cross section. Similarly, the same thing, plus the spacing is 300 divided by 26.3. This is for RIY, which is for the individual cross section. You have to put that RIY. Am I clear? Okay, now you do so, you get 1.59 into 0.957. What does it indicate? This indicates this fellow is a reduction factor. You are penalizing because it is discrete. If you run the numbers instead of 300, if you put 100, you will get a much closer number to 1. You understand what I am saying? So more the fastener spacing, greater is your reduction factor. Lesser the fastener spacing, you are closer to continuous, right? So the code inherently accepts that there is some reduction that has to be made if the fastener spacing is not continuous, it is discrete, and depending upon the spacing or the discrete distance, you have to adjust and come up with a factor. So RIY equal to 1.52. Now I run this number, PCREY is this, instead of IY 1.59, I put 1.52 and I get this value. which is 939.93. Now, which one is PCRE? Is it PT or PCREX or PCREY? You have to find out the minimum. Right? So, minimum of PT, PCREX and PCREY, you get PT 170.88 is the one that governs. Right? Now, you got PCRE. The question is, so what? We have to know why we are doing what we are doing, right? So, what do we do here? So, we get from PCRE, we get FCRE because FCRE is PCRE by AG, 70.88 into 10 power 3 divided by 1435.18. We get 491.14 MPa, which is FCRE. Right? Why should I calculate FCRE? That's the question. Why should I calculate FCRE?
That will be the maximum low local stress.
Now, what does critical mean, FCRE? Whenever they say critical, what does it mean, critical, CR? Huh?
Minimum load or stress which will lead to the failure of the member. You say that it is critical stress.
It is not minimum, no. How is 494 minimum? It is exceeding the yield, right? What is the yield for this problem? 450 something? What is the yield stress? 350 is the yield stress. So according to your logic, it is exceeding the yield stress. How is it correct? FCRE is a fictitious value. It is the farthest from the truth. Right? But we have to understand FCRE in order to understand. Right? So you have to first calculate FCRE. What is the meaning of FCRE? FCRE means it is the critical buckling stress which does not include imperfections, geometry, residual stress, everything in a utopia. Now, you know, utopia is a very idealized, there is also another word called Shangri-La. You can go look at it. It's a very idealized world, everything would be perfect. Right? That represents FCRE. But that cannot be used for design. But unfortunately, the design equations contain FCRE. So in order to reach the design, we have to go through this. Right? So that's why we calculate FCRE. So the nominal axial strength, the P&E, for yielding and global buckling, we have to calculate Fn. Right? Which is the nominal compressive stress. The nominal compressive stress, right, is given by this equation. Right? This equation in chapter E says that if the lambda sub c is less than or equal to 1.5, you use the topmost equation, 0.658 lambda c square into Fy. If lambda sub c is greater than 1.5, Fn equal to 0.877 divided by lambda sub c the whole square by Fy. So what is it? 1 by lambda sub c square. Does it ring a bell? When something slenderness square is in the denominator, does it ring a bell? What does it look like curve?
Phi square is reduce from ideal curve will reduce for imperfection and
Now what is that? It's a parabola. I'm simply asking mathematics. Never forget your high school teacher ever in your life, especially your math teacher. He is more than God. I'm telling you. If people in high school teach mathematics perfectly, I don't think there will be any shortage of engineers in our country. Math is the foundation for everything. Right? So 1 by lambda sub c square indicates it's a parabola. So it means that when you exceed the Lakshman Rekha of 1.5, you have to use Euler buckling. Right? 1.5 is the cutoff. When it is less than that, you have to use this equation. Now, I don't know which equation to use. Should I use the top one or should I use the bottom one in order to calculate my P and E, which is AG into Fm. But to know that, I need to know lambda. So that's why I need to use this equation. Lambda sub c is given as root of F4 by FCRE. So in order to arrive at which equation I should use, I should calculate lambda. In order to calculate lambda, I need to have FCRE. You understand? To calculate FCRE, I have to calculate PT, PCREX and PCREY. So I have to calculate all the three values, find out the minimum, then I have to calculate FCRE. FCRE is fictitious, as I told, it is a useless parameter because it is already exceeding the yield, but still it is required because I have to choose between devil and the deep blue sea. Which one should I use, the top one or the bottom one? Right? So I have to calculate this lambda sub c. It is 0.844. 0.844 is obviously what? Less than 1.5. So I have to use the topmost equation. So I see that Fn equal to 0.658 lambda sub c square into Fy. I do that into 350, I get 259.77 is my Fn. Once I got Fn, I'm going to multiply with Ag. Right? So Fn into Ag, I get 1453.259.7, it is 372.82 kilonewton. So 1/3 of the problem is done, which is I have calculated the nominal Euler buckling load. Now two more things are there. One is nominal local buckling load. The third one is nominal distortional buckling load. But the second one, nominal buckling, local buckling load, is little tricky. Why is it tricky? Because inside that there are two fellows are there. One fellow we can use the effective width method to arrive at. Another fellow we have to use direct strength method to arrive at, and then we'll find out what fellow to use. You understand? So it's slightly getting complicated. I want your much more undivided attention for the next 15 minutes to cover only that. I guarantee you that if you study this one, you'll be very successful in life. Okay? So please listen to me. Right? Now, nominal axial strength for local buckling interacting with global buckling. So, method 1, as I told you, two categories. First category is effective width method. So, find the effective width of all the elements. That is very simple. You have to take piece by piece. What are the several pieces here? Okay. So, here we have to look at this cross section. This cross section, if you look at it, this is a stiffened element. This is stiffened with simple lip. This is unstiffened. So, we break it into three categories. Right? The web is a stiffened element. Why is it called a stiffened element? Yes, so both sides are there. The corner is actually offering some stiffness at the top, right? This is the folded ends or folded corners. So this becomes a stiffened element. But then the same thing exists here. But why do you call not stiffened element, stiffened with simple lip? What is the meaning of that? As per your logic, this should also be stiffened. You told, as per your logic, this side also is there, corner, that's it.
Even by this web will not, lip will not give that much difference.
Right.
Length of the lip.
Huh?
Length of the lip is very
So the length of the lip attached to the gland.
Yeah, so depth of the lip, right. So, see, while I was working in the US, my boss would always ask this, how good is good and how bad is bad, right? Good and bad are very relative terms, right? What is good to you may be bad to me, and what is bad to me may be good to you, right? It is, so if you do all these things, we become very philosophical. So as engineers, we cannot be philosophical. Although we get a PhD degree, we should not be philosophical. Right? The objective is to quantify, qualify, and tell them the truth to some extent correctly. You can add load factor and other things, but there should be some truth in what we say, right? Here, we really don't know how much amount of depth I need in order to make it stiffen. So without knowing that, how can I say that? So I am saying that it is stiffened with simple lip, but I really don't know what it is. But one thing for sure is that this lip fellow obviously is unstiffened because it's free, right? So that is very sure. So now my objective is to find out each piece, right? So piece number 1 is this stiffened. Piece number 2 is partially stiffened, which is the flange. The piece number 3 is unstiffened. The piece number 4 is the 4 corners, which is very effective, so it is fully effective. So you can carry out the cross section, multiply by the thickness, multiply by yield stress, you get. value. Because of the bend thing, right? It's actually very, very strong. So you don't have to worry about it. It is 100% fully effective, right? Any questions on this one? Good. Now, we know that in order to calculate all these things, we have to calculate the slenderness ratio, right? The slenderness ratio is given by this equation 1.052 divided by root k into W by T into root of Fn by E. Okay, Oma? Correct? Everybody right? Here 1.52 is a number. WT is the width. What width? Flat width, not B. Flat width without chopping everything. Right? You go to mutton shop, what they'll give everything. You have to say remove this one, I want only. Right? Like that you have to remove all the garbages. Only thing I want is the flat width. Next, what do you need here? This one is the T. Thickness is the base metal thickness, which we know. E is what? Fn is? We have already calculated in the previous one, right? So nominal, right? So we need everything. The only fellow we don't know is K. What is K?
Plate buckling coefficient.
Huh?
Plate buckling.
Elastic plate buckling coefficient. Don't say plate buckling coefficient. This elastic plate buckling coefficient. Okay? Now we have to do this one. Our objective now is to calculate K. Okay? K is very simple. Okay? For stiffened web. K equal to 4. We know that for all four sides simply supported, K equal to 4. So we put K equal to 4. What do we get here? We get 1.847. Right? So we know the Fn equal to 259.77. E is this. When we run the numbers, right? We can find out lambda. Right? Since lambda equal to 1.847, which is obviously greater than 0.673, we have to choose a reduction factor based on this one. So the reduction factor is given by 1 minus 0.22 by lambda divided by lambda. This I am sure you are aware of this one by the tutorials, right? So this is the reduction factor for web. So we have 1 minus 0.22 divided by lambda equal to 0.477, the reduction factor. So what do we do here? Reduction factor into W. What does it mean? Only 47.7% is effective. Rest is going out. So it is not effective. Right? Now we have this one. When we do so, out of 192.12, 91.64 is effective. So that is B effective web. Right? So we got it for this one. Next one is the flanges. Right? When we have to do for flanges, what do we do here? We have to find out the flange. As I told you, flange, we really don't know whether the depth of the lip is sufficient to act as a simply supported case. Right? So we need to find out what is that. Right? So in order to do so, we have to do some calculation. So if we have to find out the flat width by thickness, and it should be less than or equal to 0.328s, we have some equations. If the flat width by thickness is greater than 0.328s, we have some more equations, right? Now, the question is, what is S? Right? So, S is given as 1.28 into root of E by F. Right? So, 1.28 into root of E by F is equal to, that F is nothing but the nominal stress that we previously calculated, Fn. So, Fn equal to 259.77 from global buckling. So when we put that 1.28 into root of 2.03 into 10 power 5 divided by 259, we get 35.78 is the S. Right. Now what is 0.328S? Is given as 11.74. Right? So we have to calculate this. Our objective is to find out which equation to use, top equation or bottom equation. To find out that, we have to calculate W by T, and we wanted to know whether it is less than or equal to 0.328s. So when you do so, we see that W by T equal to 67.12. You go to the back previous one, you will see that flat width is 67.12 divided by thickness is 1.957. You get 34.29. That's the W by T. Right? So you got this one, you got 34.29. 34.29 is obviously greater than 11.74. So we come to this part. So this is the equation that we should use. Correct? So when we have to use this equation, what do we do here? We have to find out now one more thing. What is the moment of inertia that is required? What is the moment of inertia that we have supplied? That IA is the moment of inertia that is required to act as a stiffener, right? So that is a bigger equation here. This is 399 into t power 4 divided by W by T by S minus 0.328 the whole cube, and it should be less than or equal to t power 4 into 115 into W by T by S plus S. Right? So we calculate this one, that is the required moment of inertia. Now that is required, and then we also have to calculate what is IS, right? What is the moment of inertia, unreduced moment of inertia about its parallel axis. We'll come to this one. This is the provided moment of inertia. So this is required, this is what is provided. We'll find out the equations for both. But before we go, so we have to find out what is RI. RI is the ratio between the provided and the required. Provided by required is the ratio RI, and it should be less than or equal to 1. It cannot be greater than 1, right? You cannot take more money from the bank than you have. If you have 100 rupees, you can take 90 rupees, 95, at the max you can take 100. Right? You cannot take 105, 110. That's what it is trying to say. Right? Now, let's calculate this one. So you have this equation, Ri should be Is less than Ia. Now, Is less than Ia, what is the value here? We have to calculate Ia first. So Ia is given by 399 t power 4 W by T by S minus 0.328. So when we run the numbers, we know that S equal to 35.78. We already calculated W by T is equal to 34.29 from the previous step. So and it should be less than this value also, right? So when we run the numbers, we get Ia equal to 1465.87, and it is less than 1689. So we can use this equation. Otherwise, we have to use only this one. It cannot be greater than 1. So this number is 1465, less than this, so it is okay. So Ia equal to 1465. This is what is required to act as a simple support so that K can be 4. Right? But we cannot come to that conclusion because we have to calculate IS. Right? So what is IS provided is given by d cube t into sine square theta divided by 12. Right? So this one is 11.04 is the depth of the lip into cube into the thickness 1.957. Sine square theta is sine square 90 because it is actually 90 degrees, right? So divided by 12. When we do so, this is the value that we get, right? So here it is also used for some 45 degree stiffness, in which case you can put the angle, right? But in our case it is 90 degrees. So we get IS equal to 219.77.44 millimeter cube, which is much less than 14 something, right? Provided, so you see that 1465 is at the one, so this is 0.149 less than 1. So obviously we do not have much stiffness for the stiffener to act as a stiffener, right? So how stiff is stiff? It's not really stiff, right? So we need to do something else. So what is that? We have to find out the elastic buckling coefficient K based on this d by t less than 0.25 or d by t between 0.25 and 0.8. Right? So what is d by w? So for which we have to calculate d by w. Okay. And based on d by w, you can choose this equation or choose this equation. But if you choose this equation, say for example, you have to calculate Ri and N. N is given as 0.582 minus W by T by 4S, and it should be greater than or equal to 1 by 3. So d by W is 0.22. D is the depth of the lip. W is the flat width of the flange. This is not the flat portion. D is the full depth. 15 minus just the coating thickness you are taking. So don't get confused. Don't reduce the corner radius for this one. As per the code, you understand, many people make that mistake. Don't take the corner radius out. Right? Here the corner radius is included, which is the total depth of the lip divided by the flat width of the flange is 0.22. Now this is less than 0.25. Since it is less than 0.25, I have to use this equation here. Right? 3.57 RAN. Right? So now, to use this equation, I have to calculate N. Right? N equal to 0.582 into W by T by 4S. It should be greater than or equal to 1 by 3. So this becomes 0.342, it is greater than 0.33, so it cannot be more than, it has to be more than this one. So this value should be 0.342, right? So we got N equal to 0.342. Now we already know Ri. So Ri is 0.149. So when we put it, K equal to 3.57 Ri power N plus 0.43 and should be less than 4. What is the meaning of this equation? This equation is telling you something. What is the meaning of this equation? What does the right hand side say? So maximum is 4. So madam is saying maximum is 4. That is correct. So it cannot exceed 4. Right, but why 0.43?
100 is free for 100.
Exactly. So not one end, 3 ends are simply supported and one end is free in a plate, right? But you usually take the 2 ends, loaded edges are simply supported, usually, right? And then you take the free end, the unloaded edges as one side is simply supported and one side is free. If that is the case, you have K equal to 0.425. The code has rounded off to 0.43. So it says that the worst case, you will get 0.43. Right? And this is the extra thing that you get because of this small thoda stiffener. You understand? So it says that it's not 100% free, it is not 100% simple support, it is somewhere in between. Our job is to not neglect the depth of the stiffener. We take that and do some calculations so that we get some value of K which is greater than 0.43 but less than 4. Right? That's what this equation is trying to tell you. So we have this one, so when we run the numbers we get 2.29, right, which is great. Right? It's not as great as 4, but it is not as bad as 0.43. Right? So we got a value of K. Why did I find out K? I forgot. Why should we find out K? Why? I forgot. Why did we find out? Elastic buckling coefficient, why? To find out the effective width. No. Slenderness of the member. Because that lambda sub C tells you the slenderness. Based on the slenderness, I have to determine which equation should I use. Right? So that's why I have to find out this. So now, I got this one. So this is 2.29. So I can find out the slenderness is 0.853. So this is the, everything is known except K, you put 2.29, right, you get 0.853, which is your lambda, slenderness ratio, right? So when we run the numbers, we know that it is 0.853 is greater than 0.673, right? So I have to use the equation down, right? Why it is, why let me ask you something. What is this 0.673 and what is this one and why is this one? Why when it is greater than this one you have this? When the slenderness is so short, right, less than 0.673, you say that it is 100% effective. That's why there is a reduction factor is 1. Otherwise, the reduction factor will be more. So, depending upon the slenderness, right? You know why Super C came into picture? Super C. You know what Super C is? Yeah, Super C is one. I think the original thinker of Super C is, I think, is Greg Hancock, Professor Greg Hancock. So, the two stiffeners. The reason is that when the depth of the stiffener, depth of the web is too much, it always fails in local buckling. So, when you put 2 Super C, then you can reduce your, slenderness. That way you can actually increase the capacity by bypassing local buckling. So similarly, this one, right, when the slenderness is low, less than 0.673, it is 1. When it is greater than that, you have to use the reduction factor. So you use the reduction factor, you get a value of 0.87. So which means that 87% of your flange width is effective. So what is your flange width? 67.12, right? So 67.12 into 0.87 is 58.39 is effective, right? Now we have done this one. What else do we need to do? There are 3 things, right? We have the depth of the stiffener, not the stiffener, web fully stiffened, flanges partially stiffened, unstiffened is lip, right? So we have to now go to the unstiffened portion, which is effective width of the lip. If you look at lip, the flat width is 11.04, right? Don't get confused with the total depth, which is 15 something. That is only for calculating W by D. No? Okay, so this flat width is here, lip, 0.43, right? So when you do so, you get 0.324, right? 0.324 is what? Less than 0.673. Right? 0.324 is less than 0.673. It means that the row lip is 1. But the code says that even though it is 100% this one, because it is lip with one side unstiffened, you cannot take 100% advantage. You have to put a reduction factor. The reduction factor is given by this one, which is the effective width of the stiffened is calculated. So this means that it's not this ds dash is basically 1 into 11.04, but actual ds is given as ds dash into ri. Ri is 0.14 something, right? 0.149. It says that you have to multiply. You understand? We calculated where we said that lambda 0.324, row lip is 1, right? We see that everything is fine and dandy, but it's not the case. It says that you are only calculating row lip into B is ds dash. The real ds is you have to multiply by ri. Ri is the ratio between the what I have as stiffness and what I require as stiffness, right? That ratio between is and ia is your ri, right? That value is 0.149, so you have to multiply by that and you get 1.64, right? So you have this one. So you have here, how many things you have? You have 2 webs, right? 4 flanges, 4 lips, 8 corners. Corners are fully effective. So the effective width of that is 4.62, right? That you have to do as a circle and 1 quadrant, right? 1/4 of that. You have done all that stuff, right? So when you do so, you get the summation as 460.36. The thickness is the same. You multiply, you get 900.92, right? Right? So when you do so, what do you get here? You got the area, and then you find out the local buckling strength by multiplying with Fn. So A effective area is 900 into Fn we calculated 259.77, you get 234. Excuse me. So you get PNL equal to 234.03. Is that the end of story? Obviously not. No, not distortion. You have to calculate DSM. And we only that's why I said no, there are 2 branches of families inside local buckling. One is this one and another is this one. We have just done it using effective width method. Now we have to do it with DSM. Good job. Man, I thought you guys should be sleeping, man. Good. And now the next one is method 2, which is the direct string method. So in direct string method, for a single section, we have all these things. right? Local buckling is given as k into pi square e divided by 12 into 1 minus nu square into b by t the whole square, right? When it comes to top, it becomes t by b or t by w the whole square. So this, for web, we know that it is 4, so the value is 76.15. For flange, we know that k is 2.29, you get 357. For lip, it is 0.43, so when you do so, you get, right? So the lowest one is 76.15. So the web buckles first before the flanges and the lip, right? That's the meaning of this. So FCRL is 76.15. Right? Now you multiply this one with the AG, you get PCRL equal to 109.29. So PCRL is critical local buckling
Stress.
load amma PP na load. Now let me ask you, what is the difference between effective width method and DSM?
In effective method, we will reduce the area instead of reducing the stress. DSM will reduce the stress, will keep the area same.
We'll reduce the stress, right? So, is correct. So, in effective width method, we are finding out the sections that are effective, multiplying by the nominal strength, right? And then in DSM, we don't reduce the area, we take the A gross and multiply by this FCRL and you get this one, right? That is the difference between one place you are actually reducing the area, right, and keeping the stress as very high. Another place you are actually keeping the area and instead of FN you are putting FCRL. That is the difference between this. So now you have to find out, in order to, we only found out PCRL. Is PCRL useful? No. My job is to find out P and L. But PCRL is a fictitious value. But fictitious means what? Fiction. Right? When people say fantastic, what does it mean actually? It's fantastic movie, yeah, it was nice, right? They say fantastic. What is the meaning of fantastic?
Everything is perfect.
Fantastic is actually a derogatory term. Fanatic is actually fantastic, means it's not the right, but over a period of time, it gets changed. It's not true. That's what it means. Fantastic means it's exaggerated. They say that it is too good to be true. It's too good. Even when we say, instead of very good, we say too good. But when people say too good, you know what it means? It's actually false. That's why they say it's too good to be true. Right? So our objective is, now we have found out critical, right? Critical is fictitious. It's not true. Right? And we have to find out how to go from critical to this one. So what do? We go here and then we have to calculate P and L. But in order to calculate P and L, right, I have to calculate, what is that? Lambda L. In order to calculate lambda L, I need to have P critical L. Right? So our objective is to find out lambda, right? In order to calculate lambda, I need F critical L, F critical D, or F critical E, or P critical L, P critical D, and P critical E. Some fictitious value which is critical is needed in order to find out lambda. Why I should find out lambda? Because the lambda will tell me which equation to use. Once I use the equation, I'll get the value and then I'll go from there, right? So now, here P critical is 109, Pn is 372, so when we do so we get 1.847, right, which is greater than 0.776, so I have to use this equation. So Pnl equal to 1 minus 0.15 PCRL by Pne for this one on all these things, right? So I know that PCRL equal to 109.29, which I already calculated. and then you have P and E is 372, we do all this stuff into 372, we get 207.25 kilonewton, it is P and L. Right? Is this the end of story? No, because we have found out using direct strength method P and L, we have found out using DSM, we have found out P and L. We need to find out the minimum of the two. So, using effective width method 234, using DSM 207, the minimum is 207.25 P and L. So now 2/3 of the problem is done. Right? 1/3 of the problem is by finding out P and E. Don't use PCRE. P and E. Now P and L. What is remaining? P and D. Right? So that's what we are going to do. The third one is your distortional buckling strength. Right? Distortional buckling strength calculation is little nasty. Right? So you have to do a lot more calculations. So based on DSM analytical approach. Right? So this is chapter 1. You give this, all these things you have to take into consideration. He gives a lots of equations. It's very simple. If you look at it, what is PCRD? Right? You have to calculate PCRD. Why we should calculate PCRD? So that we get lambda. Right? So we need PCRD. But PCRD is given as AG into FCRD. It looks very simple. But the problem is, in order to calculate FCRD, I have to calculate 5 different parameters. That's the biggest problem. You have to calculate KFE, 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 WG. It's a very big equation, you have to do so. Right? And each one of them is actually having a elastic rotational provided by the flange to the flange web juncture and elastic rotational stiffness provided by the web to the flange web juncture. All these things have to be taken into consideration. Right? So, now let's go back. So I have to calculate FCRD. For FCRD I have to calculate this, right? So what do we do after this one? I should also calculate this LD because this equation contains LD. What is LD? Is a minimum of LCRD and LM, and we have to calculate LCRD and LM. LM is the distance between the discrete restraints. In our case it is 1800, right? And then you have to calculate, this is elastic rotational stiffness, geometric rotational stiffness provided by flange, demanded by flange from flange juncture. And then there is one more thing, geometric rotational stiffness. Okay, there is one more thing here. This is the geometric rotation stiffness, right? Demanded by web from flange web juncture, right? So because of lack of real estate space, we have just put it here like this, right? So we need to calculate all the 4 parameters. This KFE is actually an additional stiffness that is being provided. If there is a juncture at that point, most likely it is always 0 because we don't provide juncture at that point. So we don't take that into consideration. So we take 1, 2, 3, 4 parameters we have to calculate, right? So now we have to find out the geometric flange plus lip properties of the channel section. Why? Because there are equations in the codal provisions for which you have to calculate using only the centerline stiffness method, right? The centerline stiffness method, the H is 199.696 minus T, right? So what is T? T is 1.957. So this is 199.96 minus T by 2 at the top, minus T by 2 at the bottom becomes T. So when you do so, you get 198. This B is 74.96 minus T, and then this D is equal to 14.957 minus T by 2. Right? You get these values. Now why I calculate these values? Because the codal provision gives you some formulas to calculate that based on the centerline stiffness, centerline method. Right? So now you have 2 back-to-back centerline channel sections. So what do I do here? I go to the appendix table 2. It's very simple. AF, JF, IXD, IXF, everything you can calculate using centerline method, right? You have done that. Now, what do we do here? So we go to the single section, we have all these values. When we do all these calculations, it comes out to be 170.22 up to these values. All the values can be calculated. Why I should calculate all these values? Because in order to calculate the 4 different parameters that I told you, right? These values are essential. This is the input parameters. So, you have this KWE ETQ by 12 into 1 minus mu square 2 by H naught, this value, all these values. H naught is the total depth of the section, so you can do all these things. Here you have another value here, LD. LD is given as minimum of LCRD and LM. So you have to calculate LCRD. There is an equation for this when you calculate 502.44, and LM is the distance between discrete restraints, which is 1800. The minimum of the two is 502.45. So that is the value you have to use here, right? Here and here and here, in order to calculate KFE, FE and KFE, FG, right? For KFE, WU, you don't have to worry about it. It is very simple. You can just use this. So I calculated web and flange. Right? So you have this third equation, you put this values here. This is 2056.22, and then you have this next one, KFEWE. Okay, KFEWE is 1393.58, plus the third one is 0, plus divided by 114.88 plus 10.19, you get FCRD equal to 137.6 MPa. Right? So you got the value of FCRD. So what do we do here? Now you multiply, you have to find out PCRD, you multiply by A gross, right? So this A gross is given as this one. The distortional buckling load is assumed to be the sum of individual C sections. So you multiply by 2. So because this is for one section, 2 area, 2 into AGI into FCRD is 137.6, and you get a value of 197.48, which is PCRD. But that is not sufficient, because we want to find out PND, not PCRD. Always critical is fictitious. That is not true. But we have to do that because to calculate slenderness. Only if we calculate slenderness, we know which equation to use. Only after that we can find out the value. Right? So our nominal axial strength is given by this equation. This is the equation, so we don't know which to use, whether the top one or the bottom one. So let's calculate lambda d. Lambda d is given by Py by PCRD, right, which is 5a. So PCRD is given as 197.48, right? So Py by PCRD is Ag Fy, which is the total area of the cross section into 350, which is Py, which corresponds to yield load, divided by 197.48 into 10 power 3, you get 1.595 greater than 0.561. So you have to use this equation, right? So you got the second one. Now what do we do here? That is equation number 5, right? Hello, sir. Hello. Sir. Hello, sir. Please. Yeah. Sure, sir. Sir, this, Baji, yeah, 2 days back, sir, they were interested in actually doing this one, which is basically plantation. I said we need more of solar. So they said that we are actually in solar business only, because electrical. So they said they will be very happy to do that. Yes, sir. Yes, sir. Exactly, sir. Exactly. Sure, sir. Sure, sir. Sure. Sure, sir. Sure. Let me solve this. So now we got Py by PCRD, right? So we have calculated PCRD. We got this equation. We are going to this equation. So we have 1 minus 0.25 into PCRD is 197.48 divided by 1434.18. We do all this stuff. 245.92 kilonewton. So the third portion is also done. The first portion is PNE. The second portion is PNL. The third portion is PND. Now which one is going to govern? We'll find out the minimum, right? So the distortion buckling strength is 245.92. So we have this one 372.82, 207.2, this one. So the local buckling is going to govern. So this is the failure load. Is that all? Then we have to put safety factor, right? So we have to also put safety factors. So the safety factor according to this one is 1.8. You put it, you get 115. Or you can do by LRFD, you can get 176.16. Right? So this is the safety factor that we have to use in our values. Questions, comments? That's it, I guess. Thank you so much.